In this example, we will examine a rigid body problem involving a linkage. In the linkage shown here, link AO rotates with a constant angular velocity, omega AO, of 10 radians per second in the counterclockwise direction. Link AO is 0.1 meters in length, link AB is 0.26 meters in length, link BC is 0.18 meters in length. The distance between points O and C is 0.18 meters. When point A is located 0.06 meters to the left and 0.08 meters above point O, link BC is vertical. At this instant, what is alpha AB, which is the angular acceleration of link AB? Identify your coordinate system and label the positive direction of your coordinates. In this case, a rectangular coordinate system is more convenient. Indicate the positive direction of rotation. The angular acceleration of link AB appears in the equation relating the acceleration of points A and B. The acceleration of point A is equal to the acceleration of point B plus the acceleration of point A relative to B. This is equation 1. The relative acceleration term is decomposed into tangential and normal components. The tangential component is alpha AB cross RAB, the position vector pointing from point B toward point A. The normal component is the angular velocity of link AB, called omega AB, cross the quantity omega AB cross RAB. The angular acceleration vector for link AB has a magnitude of alpha AB and points in the z direction. The angular velocity vector for link AB has the magnitude of omega AB and points in the z direction. RAB starts at point B and terminates at point A. Point A is located 0.24 meters to the left and 0.1 meters downward from point B. In order to find alpha AB, we need to obtain omega AB, the acceleration vector for point A, and the acceleration vector for point B. Omega AB is obtained by relating the velocity of points A and B. The velocity of point A is equal to the velocity of point B plus the velocity of point A relative to point B. We do not know the velocity of points A and B, but we can find expressions for them by relating those velocities to the velocity at points O and C. The velocity of point A is equal to the velocity of point O plus VAO, the velocity of point A relative to point O. The velocity of point O is 0, and the relative velocity is rewritten as omega AO cross RAO, the position vector pointing from point O toward point A. The angular velocity vector for link AO has the magnitude of 10 radians per second and points in the positive z direction. RAO starts at point O and terminates at point A. Point A is located 0.06 meters to the left and 0.08 meters upward from point O. Take the cross product of omega AO and RAO to obtain the velocity of point A. The velocity of point B is equal to the velocity of point C plus VBC, the velocity of point B relative to point C. The velocity of point C is 0, and the relative velocity is rewritten as omega BC cross RBC, the position vector pointing from point C toward point B. The angular velocity vector for link BC is omega BC and points in the z direction. RBC starts at point C and terminates at point B. Point B is located 0.18 meters upward from point C. Take the cross product of omega BC and RBC to obtain the velocity of point B. Now we turn our attention to the last term in equation 2, VAB. VAB is rewritten as omega AB cross RAB. We already found expressions for omega AB and RAB and can evaluate their cross product. Plug in all the velocities into equation 2, equating the x terms and the y terms. We obtain two equations and two unknowns. Link AB rotates in the counterclockwise direction at a rate of 2.5 radians per second. Link BC also rotates in the counterclockwise direction, but at a rate of 5.833 radians per second. The acceleration of point A is obtained by relating the acceleration of points A and O. The acceleration of point A is equal to the acceleration of point O plus the acceleration of point A relative to point O. The acceleration of point O is 0 since it is fixed. The relative acceleration term is decomposed into tangential and normal components. The tangential component is alpha AO cross RAO. The normal component is omega AO cross the quantity omega AO cross RAO. Alpha AO is 0 because link AO rotates with constant angular velocity. We already found expressions for omega AO and RAO. Evaluating the cross product gives us the acceleration of point A. The acceleration of point B is obtained by relating the acceleration of points B and C. The acceleration of point B is equal to the acceleration of point C plus the acceleration of point B relative to point C. The acceleration of point C is 0 since it is fixed. The relative acceleration term is decomposed into tangential and normal components. The tangential component is the angular acceleration of link BC cross RBC. The normal component is omega BC cross the quantity omega BC cross RBC. The angular acceleration vector for link BC has the magnitude of alpha BC and points in the z direction. We already obtained expressions for omega BC and RBC. Evaluating the cross product gives us the acceleration of point B. Plugging in all the expressions into equation 1 and evaluating the cross products gives us the following equation. Equating the x terms and the y terms, we obtain two equations and two unknowns, and can solve for the angular acceleration of link AB and link BC. The angular acceleration of link AB is 10.42 radians per second squared in the counterclockwise direction. The angular acceleration of link BC is 19.21 radians per second squared in the clockwise direction.